I will make sure you get your full time, Olimpia. So now Olimpia and Sebastian in their joint paper, take it away, please.
Thanks, Vanessa and Alex, because their talk will make this one very easy, because many things were already said, even if the conclusions will be completely different, but the presentation of the problem is pretty the same. So we will focus on one particular problem related with the problem of molecular structure, that is problem of isomerism. We will see how isomers are treated in chemistry, where in physics, and some conclusions. First, this problem belongs to the questions about the relationship between chemistry and physics, and in this field, the problem of the molecular structure is central, and the problem can be expressed with a question: can molecular structure be explained exclusively in quantum terms? The first question is, what is molecular structure? That is something that must be explicitly. There are at least three different concepts of molecular structure in molecular chemistry. Refers to the spatial arrangement of the atoms in the molecule and the chemical bonds that hold them together. If we go to quantum chemistry, a first approximation from the view of quantum chemistry, a molecule is a system in physical space composed by nuclei surrounded by inert inner shell electrons placed in different definite positions, and bonds explained in terms of interacting bonded electrons. And the structure of this system is defined by these elements in their spatial arrangement. This is a characterization that comes mainly from Brian Sutcliffe. Or we can go to a more quantum, if you want, characterization of molecular structure. And from this view, a molecule is a system in which the nucleus are placed in definite positions, constitute a potential in which quantum electrons move. And the structure of this system is defined by these elements in their spatial arrangement. This is something that is implicit in Hans Priemann's works. The point we want to make is that in any case, in the three characterizations, the concept of molecular structure involves a strong spatial connotation regarding at least the positions of the nuclei. So we need to give an account of those positions to give an account of molecular structure. In this case, we will focus on the problem of isomer. So the question is, can isomerism be explained exclusively in quantum terms? This is the precise question. How isomers are conceived in chemistry? Well, we know that our molecules will be identical for molecular formula. That is the same number of atoms of each element, but different arrangements of those atoms in space. And in this field, each isomer is described by his effective Hamiltonian, configurational Hamiltonian in Henry's terminology. And this Hamiltonian arises as the result of the Born-Oppenheimer approximation. I will tell very quickly how it works. I have the Coulombic Hamiltonian or resultant Hamiltonian in Henry's terminology, which has a lot of symmetries. The first step is to clump the nuclei at definite points. So these variables that have hats, they are operators, become parameters, numbers, and fixed numbers. So the first step is to have the Schrödinger equation with these parameters and to obtain the ground state energy in this Schrödinger equation. The third step is to compute this energy for different configurations, different positions, different numbers for these parameters, and so we obtain the effective potential of that molecule, and then, well, we obtain the Hamiltonian of the nuclei, and with the Hamiltonian of the nuclei, we obtain the effective Hamiltonian, I mean, the configurational Hamiltonian that is not Coulombic anymore. And so it has the original symmetries that the Coulombic Hamiltonian had. So in chemistry, each Hamiltonian is described by his own Hamiltonian, effective Hamiltonian. So isomers are treated as different systems, not as the same system in different states, but as different systems. And this is pretty reasonable, because from the chemical viewpoint, isomers are different and have different properties. So it's reasonable to treat them as different systems, different, of course, kind of systems. What happened with isomers in physics? This is a problem that goes beyond the Born-Oppenheimer approximation. Let us see the Coulombic Hamiltonian with all his symmetries. The interesting point is that this Hamiltonian is the same for all isomers, and this is what Vanessa and Alex were saying, and I will focus on this point. Why they are the same for all isomers? Because the R's, the little r's and the big R's are not scalars, are not numbers, are not functions, but are operators. So they have no definite values. They don't express definite positions in space. They are operators which have many possible values. Let us see this in a very simple example. Let us suppose that we have three particles, yes, with different masses and different charge. If we think that the particles are in this spatial configuration, we imagine, because from the quantum viewpoint we cannot put the particles in a definite positions, we have this Hamiltonian that only depends on the difference of the operator positions of the three particles. If we imagine that this is the configuration, which is the Hamiltonian, the quantum Hamiltonian, the Coulombic Hamiltonian, is the same, absolutely the same. And for any position, the Hamiltonian is the same, because the Hamiltonian, the quantum, the Coulombic Hamiltonian, the resultant Hamiltonian, is blind to the particle's position, because the elements that take part are operators. Okay, if this is the case, the Hamiltonian, the Coulombic, the resultant Hamiltonian, is symmetric with respect to the different spatial configurations. I can imagine the nuclei, for instance, in all the possible configurations, and the Hamiltonian is the same. So, if the Hamiltonian has symmetry, mathematically we know that the eigenstates of that Hamiltonian must have the same symmetry. This means that the ground state of the molecule, from the quantum viewpoint, the ground state has the same symmetries as the Coulombic Hamiltonian. Yeah? So now we can go to the view of Vanessa and Alex. Why we cannot think that the symmetric ground state is a superposition of the asymmetric states corresponding to the isomers? The idea is the following. This is the Schrödinger equation. We obtain the ground state, and we consider that the ground state is a superposition. Yes, it's a sum of all the isometric states. We are supposing that this states, these vectors, these states are correspond to the asymmetric isomers, and when we sum all of them, we obtain the symmetric ground state that needs to be symmetric because it is the ground state, it is the naked state of the symmetric Hamiltonian. So the idea here is that each isomer corresponds to a state, not to a system. Isomers should be treated at different states of the same system. This is completely different than in the case of chemistry. Well, now let us make another intermezzo. When I want to reconstruct a symmetry, I need to superpose all the possible asymmetries with equal weight. So if I have this figure, I have to superpose the two possible figures with the same weight to obtain the symmetric figure. This is a parity symmetry. If I have this segment and I want to reconstruct something that is rotational symmetry, rotationally symmetric, I have to superpose all the possible asymmetries to reconstruct the rotational symmetry. So in this case, I need to sum here all the mathematical possible configurations with the same weight, with the same coefficients. The coefficients should be all equal. The problem is that given the number and the types of the element composing a molecule, in general, only a few nuclear configurations are experimentally measured. That is, only few isomers are considered effectively real. I mean, if I suppose that this could be solved through a solution of the measurement problem, I should obtain, because if not, something is wrong, because no matter which interpretation you take, if you have a superposition with many possibilities, in principle infinite possibilities, all of them with the same weight, you should obtain by measurement all these possibilities with the same frequency. If not, there is something wrong in your account of the situation. I mean, this is it, and does not depend on the particular interpretation you take. This is plain quantum mechanics from the very, I mean, phenomenological viewpoint. So the problem here is when I measure, I only find how many? 3, 4, 5 isomers, but not all the possible mathematical configurations of possible positions of the nuclei, at least of the nuclei in physical space. And there is something more, a further remark. This state, let us suppose that I assume that it is an isomer is represented by an asymmetric state, which is in a certain sense an eigen state of the effective Hamiltonian, but it's a Hamiltonian of another different system. In this system, from the quantum mechanical view, this is not an eigen state of the Coulombic Hamiltonian, of the resultant Hamiltonian. If it is not, so this state will immediately evolve to different states. So how can I explain the stable situation of an isomer? This is something that Clavery and Diener says very clear. How can we explain that in the course of time, these initial localized states retain their localized character? Even if we are prepared to concede that the localized state different from the molecular eigenstate has been created by this interaction, the molecular Hamiltonian alone is unable to maintain this localized character in the course of time. Conclusions. The conclusion is very simple, it's very easy, is that if we have the problem of the molecular structure, the isomers put really strong obstacles to explain molecules exclusively in quantum terms. Even if we consider not isolated, that the molecules are not isolated and are subjected to measurement, because I accepting that, I'm asking myself, how if I understand this situation as a superposition, and that when I measure, one of the possibilities arise. Well, I think that isomers cannot be explained even if we consider this possibility of opening the system, the molecular system, to measurement. Thank you.
Thank you very much, Olimpia. And the first question is from Vanessa. Go ahead, please.
I think Sukumar is first, actually.
Oh, is that right? My apologies. Sukumar is first. Yep.
Okay, we might have the same question anyway. So I don't see why the isomers which are not symmetrically related have to appear with the same coefficients. I think we should be careful to distinguish between what we mean by states. You clarified that in your, I think, penultimate slide when you say that there are eigenstates, which are not that the structures these will not be eigenstates of the Hamiltonian, and conversely the eigenstates of the molecular Hamiltonian will not be the eigenstates of the physics Hamiltonian. We don't even need to go to the complication of isomers. Let's just, because isomers are just the minimum energy configurations of the molecular Hamiltonian. Even if we take, let's say, hydrogen atom with 1.4 angstroms separation, R equal to 1.4, R equal to 1.3, R equal to 1.2. I mean, these are three different structures, and in the quantum physics Hamiltonian, according to your terminology, all of these will appear, and they will not appear with the same coefficients. There is no reason why they should appear with the same coefficients. That depends upon the energy and so forth, which eigenvalue we're looking at. So I don't see why.
Sorry, I understand what you say, but this reasoning about where I find the minimum of the energy, these are semi-classical reasoning. I mean, how can I find in the complete Hamiltonian this difference? I mean, if all the isomers correspond to the same Hamiltonian, and if the Hamiltonian has a given symmetry, the eigenstates mathematically, the eigenstate and the ground state in particular, must have the same symmetry. Cannot have.
They have the same symmetry, but not the same coefficients. Because the
but there is no coefficient at that moment. There is no coefficient. I'm saying only that the eigenstate, the eigenstates, the ground state is only one. Okay, this may they must have the same symmetry. Okay, if I want to make that symmetry, I want to
What do you mean same symmetry? You mean they must have the symmetry of the Hamiltonian?
I'm talking about the symmetry of the Hamiltonian, and we know that eigenstates of its Hamiltonian have the same symmetries of the Hamiltonian of which they are eigenstates. I mean, in the case of optical isomers, I cannot obtain a state that has parity asymmetry from a Hamiltonian that has parity symmetry. This is a mathematical fact. So I have no many of them. I only have one ground state. Now the question is, how can I express that only single ground state as a superposition of other asymmetric asymmetric states? This is the question. I mean, each one of them, I want to suppose, I mean, let us supposing that each one of them that we have, I mean, let us suppose that each one of them corresponds to one isomer or one isometric structure. If I want to reobtain a symmetry, I have to make a superposition of all of them with the same coefficient. And this is a mathematical fact. This is not a physical fact. This is mathematics. And the other problem is the last one I said. Even if I assume that the asymmetric state is the state of the isomer, this is not stable. But this is the second point. The first point is that these are mathematical results. These are not physical.
Okay. Let's, if we may, move on to Vanessa's question.
Thanks, Olimpia. Very, very intriguing. I'm a little bit unconvinced about the first problem you mentioned. So for some reason, I don't understand why it is a problem that we are unable to experimentally observe all possible structures and make up a superposition in our interpretation of the problem. Because let me put this, chemically speaking, right, we always observe stable structures, and we are able to observe them in a specific time scale and under very specific thermodynamic conditions. Why do we exclude that all the other possible structures aren't in principle observed under some set of conditions and for some random time scale in order to, so because chemically speaking, why would that be a problem, right? I don't see why this is a problem that we only observe some of them and not all, because if we go into a lab, the environmental conditions themselves and the time scales in which we require for something to be stable are going to restrict the possible sets of structures that we are able to observe, right?
I understand your point, but you can understand that the charge of the proof is on the side of those who said that, well, those many configurations that we never ever observe are anyway there. And so this is something that we have to explain why even in different situations, we observe this certain kind of isomers and never ever the other ones. This is something similar to the coherence. I mean, there are many situations in which you can make a system to decohere, but you have to explain why in these cases you always observe by measurement these ones and not the other ones. If this is a problem like a measurement problem, you say, well, now I put the molecule like a quantum system with a measurement device. And when I put the measurement device decides the preferred basis, and let us suppose that the preferred basis is the basis of all those possible but never seen isomers, yes? When I have the state, when I make different measurements, I have to respect the frequencies predicted by quantum mechanics. If not, something doesn't work. This is my point. And it's not so. It's not. We cannot easily to say, well, perhaps there is. No. I have a system. I have an apparatus, and I have a superposition. The superposition mathematically has to be with the same coefficient for all the possibilities. Why I don't see them? There must be, of course, very good chemical reasons. This is why I'm pluralist, not quantum.
Okay, can we have the question from Alex now, please?
All right, thanks. It was going to be very quick, just to say that the kind of question about localization is one that is directly engaged with by the decoherence literature. And so it really does talk about, you know, continual interaction with environment photons does lead to a kind of effective localization, just on the very last point you made in your talk. But I just wanted to sort of also say something a little bit more general, which is, I don't think that there's good reason to think that in any lab ever anyone prepares an equal superposition of isomers corresponding to the resultant Hamiltonian. That's not the claim. The claim is that in principle, the resolution to measuring problem, if there was such an equal superposition, would provide the mechanism for finding the particular isomers that we find. Now, the question is, there's another question, which is, why do you find what you particularly find in your lab? And that's going to involve a kind of causal chain. Well, I mean, there are asymmetries built into the processes by which I get the particular molecules that I find in the particular circumstances in which I find them. And yet there are still tunneling probabilities and other things which make us think that there are these superpositions in some sense. But I don't think that it's right to say, like, why don't we find all these different ones with equal probability in the lab? That's the kind of causal story, why we get these particular asymmetries in these contexts.
Well, my answer would say that I agree with you. If I could explain the ground state as a superposition, then I would be able to answer this with, but the problem is previous, because when I explain the ground state as a superposition, I have all these possibilities with the same weight, and this does not agree with experiment. This is our point. This is our point. We have other points, you know, regarding other views. I mean, the other situations of symmetry, but in this case, I think that is pretty serious. But well, we can discuss this just a lot.
Thank you.
This should also be discussed over coffee. Now, just to get two more questions in, if we can. Julio, would you like to ask yours?
Well, just to make an observation that's actually the same observation that I made in the last talk. We can compute tunneling probabilities and then see if we have enough time to wait to the system to thermalize to a equal superposition of all possible states. Usually not by a factor of 10 to the something. So what's the paradox? Why do we wonder that we don't find it in practice?
Perhaps you can see that, you can suppose that you have to wait up to the time of a long of the universe to wait that all the the system will explore the infinite possibilities, asymmetric possibilities. Well, I'm a really skeptical about this because it would be a very different way of explaining the measurement problem. I never seen a kind of interpretation that suppose that the measurement shows you all the components of the superposition, but only explain it, or only weighting enough. But I don't know. Perhaps I didn't understand your question.
It appears that Alex agrees with you on that point. And if you look in the chat, he says almost exactly that.
Yeah, and I also agree with Alex that we have a generation problem. What are the generation mechanism of the things that you observe? It's like protein folding. We don't find proteins in all possible local minima. We find them in the folding that the biological system generates them, and that's the way it is. That is a causal history that generates the protein in that exact folding.
I absolutely agree with you. My question is how I can explain this with quantum mechanics exclusively. This is the question. Of course, I'm not saying that there is no structure of DNA. Well, perhaps you don't know. I'm pretty pluralist. I defend the autonomy of chemistry. So there is no problem if a molecular structure cannot be explained by quantum mechanics. For me, it's not a problem at all. I mean, I'm not denying that there is molecular structure because it cannot be explained by quantum mechanics. I'm only pointing out the problems of that explanation.
Okay, let's have just one last question because we are running over time. I see Sukumar. Please put your questions in the chat. It just makes it easier to read them out in order. Sukumar, please, if you could make it quick. But
no, it was just a follow up. I don't. We can just go on to the next thing. We can continue this over coffee.
Oh, and the coffee break. We have a place.
A coffee break now. So thank you very much. This is turning out to be an intriguing session.